All right, so you should have just finished doing the sprint on page 89 in your book. I'm about to flip this page and show the answers to the sprint. Before I do that, I just want to say though that when it comes to these sprints, it's not about it being a race with the person next to you. Being super fast at math isn't the same as being super good at math. Speed can be helpful sometimes. It's nice to practice speed because when you can do something quickly, it can help you do other things quickly as well. It can help you keep up in class, and it can just kind of like train your brain to be able to do things really well. But if you didn't get them all done in that time, or you messed some up, or didn't do as many as the person next to you or whatever, don't worry about it. All I really want from you is that when we do another one of these tomorrow, you try to do a little better tomorrow than you did today. Maybe you answer one more than you did today. It's about improving yourself, not beating the person next to you. All right, so anyways, with that being said, here's the answers I got. I just did this like really quick a second ago. Let me like adjust this thing a little bit. And it might not be perfect. There's a pretty good chance there's some mistakes in here. I'm human. So go ahead and look at it for a second, compare your answers, and if there's a mistake, point it out. I mean, I won't hear you because I'm just filming this, but a couple that I thought were interesting as I went through are obviously the ones where they sum to zero. That means they're additive inverses. There was a couple where they tried to trick you into thinking they were additive inverses, like here, number 21, negative 23 and another negative 23. They add to negative 46, not zero. So they're trying to trick you there. The rest of them were fairly straightforward. I'll leave this up for just a little while longer so people can check their answers. Write how many you got correct up here on this line, and then when we do another one tomorrow, we'll see if we can everybody can beat that number, or if you got them all correct, then we'll see if you can do it again. All right, I'm gonna wait maybe like 30 more seconds or so, and then we're gonna flip to lesson 4. All right, we're going to lesson 4 in 10 seconds. 5, 4, 3, 2, 1. All right, lesson 4. So that's over on page 35. And I want to tell you what lesson 4 is essentially about. It's about these 3 rules. So let's move this up a little bit so you can see. All right, so there are 3 rules that are going to help us add integers, or really any rational numbers, quickly. So the first rule that we'll talk about is how to add 2 numbers quickly when they're both positive. And I think you'll find that one very easy. It's essentially what you've already been doing your whole life. Then there's a second rule. How do I add quickly 2 numbers if they're both negative? And that one is pretty intuitive. Intuitive means it kind of works the way you would expect it to. And so that rule might be new to some people, but it's not that hard. And then the third rule is, how do I quickly add 2 numbers if one is negative and the other is positive? Another way of saying that is that the numbers have opposite signs, like one has a positive sign, one has a negative sign. And this rule is kind of weird. It's counterintuitive, meaning it works in a way that you might not understand right away. We're going to use vector addition to sort of like examine these 3 rules one at a time to sort of help us understand how or why they work. And then your whole learning goal for this period is to like understand and know these 3 rules, so that if I'm using them in class when I'm going through a lesson with you and you see me do this rule, or sometimes people call them tricks. They're not really tricks, but let's say rule 3 is a trick for adding 2 numbers when they have opposite signs. I want you to know what I'm doing, or be able to do it yourself if you see me doing this trick. All right, so let's go through rule 1. I think you'll find that pretty easy. So it says, example 1, rule for adding integers with the same signs. So Same signs just means that they're both positive or both negative. And so we're going to start with the case where it's both positive, like I wrote over here as rule 1. And so it says represent the sum of 3 plus 5 using, remember, we're not going to call them arrows, we're going to call them vectors on the number line. And so if I want to do 3 plus 5, well, I always start at 0. I need a vector going 3 units to the right, and it's going to stop at 3. And then I start my new vector where the previous one ended, and I'm going to go 5 units to the right to model that plus 5. And so I wind up stopping at 8, and so that means that 3 plus 5 equals 8. And now I'm going to wait maybe like 2 or 3 minutes for you to just go ahead and answer questions little I through, I guess it's Roman numerals. Roman numeral 1 through Roman numeral 6. Like, just finish these questions on this page. I'll go over them with you in, I don't know, just like 90 seconds. These shouldn't take that long. All right, let me get your attention back in 5, 4, 3, 2, 1. Okay, I'm going to give everybody a few seconds to quiet back down, look up here. All right, so it says, how long is the vector? I'm not going to cross out and write vector, but I'm always going to say vector. How long is the vector that represents 3? Obviously, it's 3 units. What direction does it point? It points to the right. How long is the vector that represents 5? So it's a 5-unit vector going from 3 to 8, but it's 5 units long. So 5 units. And what direction does it point? To the right. So one thing to notice is that these two numbers here, how long the vectors are, the 3 and the 5, these are the absolute values of the numbers. The absolute value of 3 is 3, and the absolute value of 5 is 5. So the length of a vector is always the same as the absolute value of the number it represents. And so what is the sum? 8. And if you were to represent the sum using a vector, so essentially they're asking, you're representing the number 8 with a vector. Like one, instead of 2 short vectors, a 3 and a 5 to get to 8, what if you just drew one vector from 0 to 8 to represent this number 8 or this sum? How long would that vector be, and in what direction would it point? Well, it would be 8 units to the right. And so they want you to see how these two smaller vectors that represent the addends, this is kind of an important word for this lesson. When you're adding numbers, each individual number that's being added is called an addend. So they want you to see how these addend vectors sort of relate to the sum vector. The number that you get when you're, after you add everything is called the sum. So it says, what is the relationship between the vector representing the number on the number line and the absolute value of the number? Oh, I forgot that this was already a question. We already explained it up there. So yeah, I already said it, but it's valuable enough to be worth repeating again, writing again. The length of a vector is the absolute value of a number, or of that number, the number that the vector is representing. So remember, the absolute value just means how far is a number from 0. And so if you're thinking about like this 5 vector, right, it's 5 units. But that same 5 is the length or the distance that the number 5 is from 0, right? Like if you could take this vector and slide it over to 0, then it would end at 5. So it represents that same distance even though it's like shifted around. All right. So the next question says, do you think that adding 2 positive numbers will always give you a greater positive number, and why? I'm going to give everybody maybe just like 30 seconds to talk about that with their groups and share your ideas. Do you think that adding 2 positive numbers will always give you a bigger, they say greater, but I'm going to say bigger positive number? Yes or no? Why? Go. I'm not going to use the timer. I'm just going to watch the clock. 30 seconds. All right, let's come back in 5, 4, 3, 2, 1. All right, so hopefully either you found this fairly self-explanatory or you had some good conversations with your neighbors, but the answer is actually yes. And so they want to know why. Well, the why kind of comes from our model here. When you have a positive number being a vector that's representing a positive number, it moves you to the right on the number line, right? Or positive numbers are always to the right of 0. And then when you add another positive number, the act of adding, if you're thinking of it in terms of these vectors, you're starting at whatever that first positive number you had was, and then you're just moving further to the right on the number line. You're getting more positive. And so this vector model right here is intended to convince you that yes, adding a positive number to another positive number just gets you a bigger positive number. So yes, you start at a positive number and then move further right when you add another positive, I'm going to abbreviate positive number as pos-num because I ran out of space. So you started a positive number, and then when you add another positive number, you just wind up moving further right on the number line, so you get a bigger positive one. So here's essentially that all boils down to essentially rule 1, what I called rule 1 in pink here. Rule 1 is what you already know and what you've been doing, is that when you add a positive number to another positive number, you just get a bigger positive number, and you don't have to think about negatives at all when you're adding positives, right? Like we don't ever accidentally say positive 3 plus positive 5 equals negative 8. We never make that mistake because we all super understand that, oh, positive plus positive, my answer is going to automatically be positive. What I'm hoping is that you can take how intuitive, meaning like easy to understand, that first rule is, and to see how the rule 2 is exactly the same, and then start having the same level of confidence working with negative numbers that you have with positive numbers. The way that you're absolutely sure that a positive plus a positive is always a positive, I want you to start being that same level of sure that a negative plus a negative is always a negative. And we're going to see that in the same way that we just looked at the last rule. So to essentially boil rule 1 down is that positive plus positive equals more positive. There's going to be a little bit more than that to rules 2 and 3. They're a little bit more technical. Let's see them. All right, so we're in rule 2 now, and I'm going to do that in blue because I wrote it in blue over here. But we're going to do essentially the same thing. Last time they asked us to do 3 plus 5 vectors. Now they want us to do -3 plus -5 vectors. So I'm going to start at 0 like I always do, and I'm going to draw my first vector 3 units to the left to get to -3. Oh, and you know what? In the previous one, I forgot to label my vectors. I'm going to label this one as -3. And then I'm going to start at -3, start a new vector, and it's going to go 5 units to the left because it's negative, and I wind up at -8. And so it's essentially the same diagram, just going to the left, right? So I want you to do the same thing we did last time. You go through, like all these questions are essentially the same as the questions we just did for rule 1, but now everything's a little bit different because it's negatives and things are pointing to the left. But see if you can answer all these questions before I go through them with you. So I want you to get all the way through Roman numeral 5 here below, and do Roman numeral 6 and 7, and see if you can answer C. So I'm going to give you a little bit of time to do that because it's kind of a lot. How about, I think 4 minutes should be fair. All right. right, let's come back in 10 seconds. 5, 4, 3, 2, 1. I'll give everybody a few seconds to focus up here. All right, so first few questions, pretty simple. How long is the vector that represents -3? Well, it's 3 units. Oh, this marker's dying. And what direction does it point? It points to the left since it's representing a negative number. And then how long is the vector that represents -5? Ooh, oh, I can't believe I've had this like mistake up here on the screen this whole time. Let's see here. I wish I had the same color marker that wasn't dying. So I wrote -8 because I knew that the sum was -8 and that vector went all the way to -8, but it was actually a -5 vector, right? This is representing the addition of -5. Super common mistake, you know. I'm sure some of you guys will make that same mistake, no big deal. So how long is the vector that represents -5? So it's 5 units. And it also points to the left because it's negative. And then the sum is -8, which I had accidentally labeled up here. So it's a good idea to draw a little dotted line from the end of your last vector to the sum. Like wherever your last vector ends, that's what the answer or the sum is. That's sort of the whole point of doing this thing, these vector models. And then also I like it if you sort of just rewrite the problem. So -3 plus -5 with the sum or with the answer on it equals -8. All right, so now if you were to represent the sum using an arrow, how long would if you were to represent the sum using a vector, how long would that vector be and what direction would it point? Well, to just represent -8 with a singular vector, you would need an 8-unit vector from 0 to -8, and so it would be 8 units long, and it would point to the left. 8 units to the left. And then it says, do you think that adding 2 negative numbers will always give you a smaller negative number, and why? So digging through here to see if I can find the same colored marker. Nope. All right, I'm going to switch to a different blue marker. So do I think that adding 2 negative numbers will always give you a smaller negative number? Well, it's the same as the previous question about whether or not adding 2 positives would get you a bigger positive. Because we start with a negative number and then adding another negative number just pushes us further left on the number line, then yeah, we're just gonna get more negative. This part might be a little confusing for some people because what do they mean by a smaller negative number? Well, it turns out that when you have, I'm hesitant to say what I want to say because it's wrong, but it feels right. Bigger negative numbers, like -10 being bigger than -8, is actually a smaller number. -10 is smaller than -8. Because when you're looking at the number line, bigger numbers, to be bigger or to be greater than, really just means to be to the right. And smaller or less than just means to be to the left. So the further left you go, the smaller the numbers are getting. Even if they feel bigger, -1,000,000 feels bigger than -10, but -1,000,000 is actually way, way smaller. So going that way means smaller or less than. So do I think that adding 2 negative numbers will give you a smaller negative number? Yes. Because you start with a negative number, which I'm going to abbreviate as negnum, and adding another negative number. This blue marker's dying too. I think this tells me that I use blue a lot in class. I like blue, and so all my blue markers are dying. Moves you, oh geez. All right, let me see if I can find another one. I guess I'll go back to the other one. It was moves you further left. And so it asks, what do both examples have in common? Well, they have in common that the addends, remember that's the two numbers, addends, had the same sign. See, the addends are the numbers you're adding. So in this case, -3 and -5 were the addends. And in this case, the 3 and the 5 are the addends. So the addends had the same sign. In this case, they're both positive. That means they have the same sign. And in this case, they're both negative. Meaning they had the same sign. And the sum's sign matched the addends sign. So what that means is, in the case where both addends were positive, the sum turned out positive. And in the case where both addends were negative, the sum turned out negative. So as far as rule 2, how do I quickly add two numbers if they are both negative? You don't have to write any of this, by the way. Like, this is more for me to just help you keep track of what's going on. So the first thing we just learned from rule 2 is that a negative plus a negative equals more negative. That's something to keep in mind, but here's the trick that comes out of that. And I'm gonna write it right here in this space. And it might be a good idea for you to write this in this space too. When adding negative numbers, you can add them as if they were positive, and then put a negative sign on I would say the sum, but I know a lot of people prefer to just say the answer. So for example, to do -3 plus -5, since they're both negative and there's no positives involved, by the way, in order to use this trick, there can't be any positive addends. Like, all the numbers you're adding have to be negative for this to work. If there's a single positive number being added as well, this trick does not work. So if I want to do -3 plus -5, I just do 3 plus 5. That's 8. Toss a negative sign at the end. The answer is -8. All right, that trick always works as long as all the numbers you're adding are negative. You can't do it if it's -3 plus -5 plus -10 plus +7. That +7 messes everything up. All right, so let's go back to page 37 where we were. And it says, decide whether the sum will be positive or negative without actually calculating the sum. So I don't want you to come up with answers here. I want you to just see that, oh, this is a negative plus a negative. That means the answer will be negative. And so you could save yourself some time and just write an N for negative and a P for positive, or maybe do a minus sign for negative and a plus sign for positive, whatever works for you. Do this real quick. Just look through these, determine whether it'll be negative or positive. I think there might be more on the back side. No. So I'm just gonna give you literally 25 seconds to do these. All right, 5, 4, 3, 2, 1. Giving everybody a few extra seconds to focus back up here. All right, so you should have seen that a positive plus a positive is going to make a positive. A negative plus a negative is going to make a negative. A negative plus a negative is going to make a negative. These are all positive, so they have to make a positive when you sum them. and these two are both negative, so their sum will be negative. All right. Just as confident as you are as seeing that a positive plus a positive, you know your answer is going to be positive, you should be just as confident doing it on the negative side of the number line. It's sort of the summary of what we've been doing. All right, so find the sum. Let's use the trick real quick. 15 plus 7, that's obviously 22. Now, negative 4 plus negative 16. Since they're both negative, I'm just going to add them as 4 plus 16, which is 20. And then I just throw a negative sign on there because they were both negative. All right, so 18 plus 64, well, that's 82. If I just did 18 plus 64, that's 82. But since they're both negative, it's negative 82. All right, and then the last one, I'm going to do this piece by piece, right? Like thinking of it this way, 205 plus 123. See, notice I'm ignoring the negative signs because they're both negative, so I know my answer is negative. 5 plus 3 is 8, 0 plus 2 is 2, 2 plus 1 is 3. So this is negative 328. All right, so now let's learn about rule 3. How do I quickly add two numbers if one is negative and the other is positive, or in other words, they have opposite signs? This is sort of the weird one. So let me do this one in green, because I wrote the rule in green on the first page. It says represent 5 plus negative 3 using arrows on the number line. So I'll start at 0, and I'll draw a vector 5 units to the right, stopping at positive 5 to represent positive 5. And then I start my next vector right where that one ended, and I draw it 3 units to the left to represent adding a negative 3. And it looks like I stop right at positive 2. So what that means is 5 plus negative 3 equals 2. All right, so we're getting a little short on time. So I want you to do the same thing we've done before. Answer questions Roman numeral I through letter B on the next page. But just because we're cutting time a little bit short, I'm going to give you only 2.5 minutes this time. All right, so I'm going to put 2 minutes on the timer, but I'll start it in about 30 seconds. Go. All right, let me get your attention back. Go and focus up here, please. So I went ahead and filled some of this out while you were working. And so these questions get a little repetitive. How long is the vector that represents 5? It's 5 units. What direction does it point? To the right. How long is the vector that represents -3? It's 3. What direction does it point? To the left. So we've got opposite signs, right? This time we've got one going to the right, one going to the left. Which vector is longer? The 5. And what is the sum? So the sum of these two numbers is 2. And if you were to represent that sum using one vector, how long would it be? And what direction would it point? It'd point 2 units to the right. All right, so let's do this again. Oops, I'm writing in black and I meant to do this whole section in green. So it says represent 4, so 4 units to the right, plus -7 on the number line. And so I go 7 units back, and I get to -3. So this was my 4, and this is my -7. So I started at 4, and I counted 7 units to the left and got to -3. And now it says in the two examples above, what is the relationship between the length of the vector representing the sum and the lengths of the arrows, vectors representing the two addends? Well, here's the big thing that the trick is all about. If I were to draw the vector just for the number 2, which remember is the sum here, I would start at 0, and I would essentially go to the end of this vector here, right? It would meet this vector. And what it's doing is it's covering this distance or this difference between the two vectors. Like this leftover space here is where the sum sort of exists. The same thing here. If I were to draw a vector that just represented -3, I could start it at 0 and go to here. And what I'm doing is I'm covering the difference between the two vectors, right? The space where there's not two vectors covering, right? This part is covered by two vectors, but this part's not, so this is where I need to cover. And what that space represents is the difference between the two numbers. Difference is when you subtract, right? This means essentially what I'm doing is if I took the 7 vector and subtracted this 4 off of it, what I'd be left is with this 3. Or if I took this 5 vector and subtracted 3 units from it for this -3 vector, I'd have 2 units left to cover. And so this trick comes down to subtraction. It's weird. You do addition using subtraction. So So in the two examples above, what is the relationship between the length of the arrow representing the sum and the lengths of the arrows representing the two addends? The length of the sum vector is the longer vector minus the shorter vector. I really mean the length of the longer vector minus the length of the shorter vector, but I'm kind of rushing right now. And what is the relationship between the direction of the vector representing the sum, so like this black vector here or this black vector here, and the direction of the vectors representing the two addends? Well, in this case, the sum vector, the black one, was going in the same direction as the -7, which is the longer of the two green addend vectors. And here, the black vector that represents the sum is going in the same direction as the 5 vector, which is the longer of the two addend vectors. So in other words, the sum always points the same direction as, oops, I can't believe I just did that, as the longer addend vector. Or in other words, the bigger of the two numbers that's being added, not thinking about positive or negative, I should say the greater absolute value. And so here is the weird rule for adding two numbers when they have opposite signs. You do bigger minus smaller. And when I say bigger and smaller, I'm talking about their absolute value, right? So below I'm going to say absolute value. So you're ignoring negative signs and positive signs. You're just looking at the numbers themselves, the digits. Then the answer is positive or negative depending on which was bigger. All right, so hopefully there's just like 1 more minute left in class so I can show you a couple of these on the next page. It's a little weird. We're gonna do subtraction in order to answer addition. So -1 plus 2, 1's negative, 1's positive. So let me do 2 minus 1, which equals 1. And then since the positive number was bigger, 2 is bigger than 1, then my answer is positive. All right, so 5 plus -9. I'm gonna do 9 minus 5, which equals 4. But then my answer is negative because the -9 is bigger in absolute value than the 5. So the answer to this one's -4. So -6 plus 3, I'm gonna do 6 minus 3, right? I'm doing the bigger number minus the smaller number, not thinking about positive or negative. That equals 3. But my answer is -3 because the 6 was bigger. I don't want you to write your work the way I'm writing it. I'm only writing it this way to show you what I'm doing. But in the future, don't write 6 minus 3 equals -3 because that's not true, right? So in fact, I'm gonna cross out these parts. All right.